start. All right. So last day we did matrix algebra. Some was easy, some was hard. And if you thought you could leave matrix multiplication in the dust, it's going to come back to haunt us today. So if you don't have that handout, they're all here. Look at all this paper. It's crazy. I remember first class, 21 people wanted printouts. Well, now I print 12 and it's too many. So this is back into, so we're back in the textbook. Chapter 5 was on matrix algebra and chapter 6 is on relations. What's very fun is chapter 7 is our last chapter on functions. Should be easy enough. And then we're done. So that's exciting. We'll see if we have time. Usually I like to throw in some trees and some graphs in there just because they're really fun. But we were told not to do that because you'll see it in 251. Do you guys take 251 or 221? I don't know, whatever. Your next math course, you'll see it. So, but maybe I'll sneak some in anyway, so we'll see. Or we take a break, I don't know. Oh yeah, haha. Test number 2 is on Monday, of course. We've got review on Friday, which means I need to crank out a practice for the test, just like I did for test 1. But making these notes took all day on Saturday, and so I'm kind of behind. But they're really good notes. So I know we were talking about it. How does it make sense? It does make sense. But making these notes took more than 6 hours for 2 hours of lecture. I know, right? Weird. So for me, it's all old news. Anyways, relations. Not quite at functions yet, but we're building up to functions, if you can believe that. Usually you start with functions in a math class, right? Input, yields and output, that kind of thing. But here we're just kind of building up slowly to it. So a relation, okay, if we have 2 sets A and B, then a relation from A into B is any subset of the Cartesian product, right? This is from way back when. The Cartesian product, which we know how to find, right? It's all the possible combinations where the first entry is from A and the second entry is from B, right? And so that's way back when. And so if we have A is 1, 2, 3 and B is 4, 5, then this set of coordinates could be a relation, right? And so we're told that this is a relation. So 1 maps to 4, 2 maps to 4, and 3 maps to 5, right? There doesn't have to be any sort of rhyme or reason to it yet. Okay? And so is a relation from A into B. So of course, the first values have to come from A, and the second values have to come from B. Okay? And so this is one of those possible relations, right? How many others are there? Kind of dusting off our set theory, right? Okay, so that would be the power set, right, of the Cartesian product. And so we'll need to remember that the cardinality of the Cartesian product, let's start there. How many possible combinations can I have? Well, that's the cardinality of A times the cardinality of B. We remember that. Times the cardinality of B. Cardinality of A is 3 and the cardinality of B is 2. And so this is going to be 6. 3 times 2 is 6. Sold. But then we want to know, okay, a relation from A into B is any subset of the Cartesian product. Okay? So you can pick and choose any subset from this Cartesian product, which any subset is, or the list of all possible subsets is the power set, right? And the power set, oops, hey, I had a feeling that was going to be a really good kind of power set. That looks kind of weird, but the power set of A times B is all possible subsets, but we wanted the cardinality of the power set, right? How many possible subsets are there? Do you remember how to find the cardinality of the power set? We have to do 2 times the cardinality of the original set. And that's why we needed the cardinality of A times B. So this becomes 2 times the cardinality of A times B, oops, which writing across is 2 to the power of 6, or 64 possible subsets. Power sets. It's been a while, right? The list of, or the set of all possible subsets. Okay. So if we have a set A, which has the elements 2, 3, 5, 6, fine. And we're going to define a relation R from A into A, right? So we're just mapping from A 2, 3, 5, 6 to another set 2, 3, 5, 6, a different set. Okay. AB, so the coordinate AB is going to be in the relation R if and only if A divides evenly into B. Okay. So you can only list these coordinates AB if the first one divides evenly into the second one. Okay. And so we're taking from 2, 3, 5, 6, and I think maybe I'll jump ahead. So often we kind of list the options like this when we're dealing with itty bitty ones like this. And so maybe that would be more helpful. We can start there, kind of set up our first A, 2, 3, 5, 6. And it's going to map to another A that looks the exact same. 2, 3, 5, 6. Now what we're going to do is for this set R, maybe I'll bump it up here. I wasn't planning on doing this drawing here, but that's okay. Maybe I'll go for a, I guess that's the green I have. Okay. Looks more neon on here, but it's actually quite normal on here, so that's weird. Maybe I'll go for a darker green. There. Huh. Okay, whatever. We're going to draw a line from the first set to the second set. Oh, price just went up. If the first element divides evenly into the second element. Okay. So the sneaky ones, of course, is 2 divides evenly into 2, right? And so let's draw that. So 2 divides evenly into 2. Does 2 go evenly into 3? No. Into 5? No, but it does go into 6. Okay. So then I'm going to draw an arrow down to 6. And then we move on to 3. Right? 3 does not divide evenly into 2, but it does divide evenly into 3. Will I run out of colors if I try to get fancy here? Maybe I'm okay. 3 does not divide evenly into 5, but it does divide evenly into 6. So I can draw that. Then, okay, I'll use pink. 5 divides evenly into 5, obviously not 2 or 3, and so I'm just going to skip those, but 5 divides evenly into 5, and 5 does not divide evenly into 6. And then the only remaining option here is that 6 divides evenly into 6. So what we can do then is we can list this as the set of coordinates in this relation. So we write R is the set. And if you wanted to, you could have jumped straight to just listing the coordinates, right? If you're able to look at this set and just kind of think about which ones divide evenly. But as you'll see, sometimes it's easier to map them out this way, but you don't have to. It's just to help. And so listing these coordinates, and maybe I'll use the colors I had. 2 divides evenly into 2, and 2 divides evenly into 6. 3 divides evenly into 3, and 3 divides evenly into 6. 5 divides evenly into 5, and 6 divides evenly into 6. Let me just count 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6.
Evenly, like matches up.
Well, funny you should ask. The relation divides. If A and B are in the set of integers where A is not 0, then we say that A divides B, which we denote by this kind of vertical bar. Okay? So A divides B if and only if there exists an integer k, so a whole number k such that A times k is equal to B, or k is B over A, right?
That one if there's no remaining.
Yeah. Right, and k is in the set of integers.
What if that's 0?
Oh, sorry, B over A. A can't be 0, B can be 0. But that's boring. Okay. So, and we've seen if and only if before, but it might be worth mentioning again because we're going to see it today. Usually we abbreviate if and only if as IFF. Only if. And so we can represent a relation as a list of coordinates or as a set of coordinates, just like this. And like we saw, sometimes it's helpful to illustrate this relation with some sort of graph, right? Where you start from and where you end up, right? They can be different sets. We had them be the same, right? But A can be different from B, and we can map from A into B with some relation R. So usually we denote with a little arrow what the name of the relation is. And that's because later on we're going to have kind of a daisy chain of relations. Okay. And so, okay. So relation notation is what we're going to use most frequently. So if S is a relation, from a set A into a set B, okay, then skipping this stuff, we usually write it as X, S, Y. So mapping from X through S into Y is kind of how I read it. Yeah.
That what? How come one doesn't fit on five? Isn't one-
Oh, in this graph? Oh, it's because this R, we don't know what the relation is. It's just a defined relation. So it's not divides or anything that we know of necessarily. It's just a relation. Yeah. So here, I'll just clarify an unknown relation R. So it's just telling us what the relation is. Takes 1 to 4, 2 to 4, and 3 to 5. Okay. So if we have S as the relation from A into B, then what we sometimes write, or what we have been writing, is that the combination or the coordinate XY is in the relation. But usually what we'll do is we'll just end up writing X, S, Y. Okay. And you can read it as I was gonna say maps too, but I take it back. I don't want to say maps, but it's how I think about it in my head. Right, maps to there, but I shouldn't say it. I shouldn't. Okay. Composition of relations. Like I said, we're gonna have this daisy chain of relations, right? And so if R is a relation from a set A into a set B, and then a new relation S can be a relation from B into a set C, right? Then the composition of R with S, which means that you have to start from A and you have to flow through B and end up in C, right? And then that would be the composition of RS, is the set of pairs of the form AC, where AC come from the Cartesian product of A by C. Okay. And AC is in this composite function, or this not functions yet, composite relation, if and only if there exists a B in B such that AB is in the relation R and BC is in the relation S. Now, most simply, what that's going to look like, kind of using our visual here, or maybe I'll just write A inside because we don't really care what they are. A, B, C. Then we're going to have this relation R followed by S. And so the composition of these things is where we go from R through S, so from A to C, using R and S as a composite relation. Okay. I didn't give us very much room. I had enough room on paper, but I guess I write big on here. So let's do an example. If A is the set 2, 3, 5, 8, and B is the set 4, 6, 16, and C is the set 1, 4, 5, 7, then R is going to be the relation divides, which we saw earlier, right? It has to divide evenly into from A into B. And let S be the relation less than or equal to, right? Equal to is kind of the main player, but less than is easy. And then just keep an eye out for the equal to from B into C. We're gonna list the elements of R and S. Oh, that's why. It just asks to list the elements of R and S. We'll start nice and slow. Should we do it with the map? I don't really have room for the map, so I can do it just by listing the set of coordinates. How? R, let's focus on R. R is the relation divides from A into B. So you ignore C and don't worry about it yet. Okay. And so any value of A that divides evenly into B makes a coordinate. So R is going to be the set of, and I just kind of work methodically, right? 2 divides evenly into 4, so that's going to be a coordinate. 2 divides evenly into 6, so that's going to be a coordinate. 2 divides evenly into 16, so that makes a coordinate, right? So already I have 3 coordinates, so I'll jot those down. 2, 6, and 2, 16. And then I move on to 3, and I see which of the values in B are divisible by 3. And so 4 is not divisible by 3. 6 is divisible by 3. And so I list 3, 6, because 3 divides 6 evenly. And not 16. Move on to 5. 5 doesn't go into any of those, 4, 6, or 16 evenly. So that's okay. Just gets excluded. What about 8? 8 goes evenly into 16, but that's it. Usually it feels like there's going to be a lot, but once you tackle the little guys, right, 2 dividing into some numbers, then it kind of dwindles typically. Let's see. I should change this color. Oops. Change it to orange, orangey glad. And then I'll do pink for the S relation. We do the same thing, but now we've got a different relation. Now we're talking about less than or equal to from B into C. And so now my first entry is from B and my second entry is from C. And so 4 is less than or equal to 4 and 5 and 7, right? So we'll tackle those first. Moving on to 6. 6 is less than or equal to 7. Just like we saw earlier, right? Kind of gonna have a lot of them to begin with and then not very many. So 6, 7. And 16 is less than or equal to none of those. So that's the end of the set. So when we talk about composition of relations, what we mean is that I could start here at 2 in R, right? From A, I could use R to get to 4, but then to get from 4, I could get to 5 through S, right? And so they kind of ding, ding, daisy chain, right? And so then in this composition, I would have 2 to 5. But we're not ready for that quite yet. We're just going to list okay, fine. We are ready for that. We're going to list the 5 compositions. Can we catch them all? Well, let's see. Let's start again methodically. right? Here I'm starting at 2 and I go to 4 and I can get to 4 again, right? So I get to 2, 4 in my composition. I can start at 2, 4 and I can go from 2 through 4 to 5. Right? I can go from 2 to 7 through 4, right? So that's composition. And from 2 to 6, I can get to 7, right? But that's it. 2 to 16, no, there's no first entry of 16 anywhere here. So that one's out. What about 3 to 6? I can get from 3 to 7 through 6, right? And then 8 to 16, again, nothing. Hopefully that was 5. I know it was 5. Let's list them. So 2 divides 4 and 4 is less than or equal to 4. Makes 2 to 4 as an entry in our composition. Next one, 2 divides 4 and 4 is less than or equal to 5, makes 2, 5 an entry in our composition. 2 divides 4 and 4 is less than or equal to 7, makes 2, 7 a value in our composition. 2 divides 6 and 6 is less than or equal to 7, makes 2, 7 a value in our composition. And finally, 3 divides 6 and 6 is less than or equal to 7, means that 3, 7 is also in our composition. Or if you prefer to do it visually, you can, right? Is there someone at the door? Oh, just looking longingly. It's fair. I would too if I could see it. We're going to go from A. We're going to list all the entries of A, 2, 3, 5, 8. I'll call this A. I'm going to list the entries of B, which is 4, 6, 16. And I'm going to list the entries of C. Which is 1, 4, 5, 7. 7. The relation R maps from A to B, and the relation S maps from B to C. Now, I like to map these out and just to confirm my work, but I really struggle with just drawing the lines, and in the composition is going to be wherever you can start at some point in A and end up at some point in C through the arrows. Okay, so let's see here. Let's map these guys out. 2 maps to 4, 2 maps to 6, and 2 maps to 16. 3 maps to 6, and 8 maps to 16. Already kind of a hot mess. This is just a mapping of R. Okay. We can do the same thing. Hopefully I have 1, 2, 3, 4, 5 arrows. 1, 2, 3, 4, 5. Good. Can do the same thing for S. 4 goes to 4, 4 goes to 5, and 4 goes to 7. and 6 goes to 7. So now the composition of RS is going to be wherever I can link these arrows. So starting at 2, going to 4, going to 4. That's one composition. Starting at 2, going to 4, going to 5, starting at 2, going to 4, going to 7. Right? It's the same thing that we were doing. It's just, I personally probably prefer this way. But if you like this way, that's fine. Because then you can go from 3 to 6 and from 6 to 7. So I'll highlight that one. That path. I can go from 2 to 6 and then 6 to 7. But like I said, I find it really difficult. It's just the 16 is the end of the road. There is no less than or equal to in C from 16. Okay. Nice. Well, any questions first? No. For each of the following relations are defined on the set P, which is the set of positive integers, right? That's from kind of day 1 stuff, or maybe day 2 stuff, I guess. Determine which of the given ordered pairs belong to R. So here's where we get some practice, mostly reading this kind of notation, right? So X is going into Y through the relation R, right? So R takes X into Y if and only if X divides Y, right? And so here, this is divides. We've seen that before. It's kind of a major player, so we had to introduce it almost right away. So the X coordinate from here, right? Of course, our coordinates are listed in X comma Y's. You know that. If the X coordinate divides the Y coordinate, then it is an entry in this relation. And if it doesn't, then it's not. Does 2 divide 3? No, it does not. Does 2 divide 4? Yes, it does. Does 2 divide 8? Yes, it does. Does 2 divide 17? No, it doesn't. That part's not hard. This part is hard, reading the kind of what is the relation? What do we want to find? What are we looking for? So XRY, if and only if X is less than or equal to Y. So now if the first entry is less than or equal to Y, then it's in the relation. And so I've got 2 is less than or equal to 3. That's good. 3 is not less than or equal to 2. No, no, no. 2 is less than or equal to 4. And 5 is less than or equal to 8. What if we get really crazy? XRY, if and only if Y is X squared. So then we need to take the X value, square it, and if that is the Y value, then it's in the relation, and if it's not, it's out. 1 squared is 1, so it's in. 2 squared is 4, so the next one, 2, 3 is out. But the next one is in, and we already said 2 squared is 4, so 2, 6 is out. Mostly just an exercise in reading this kind of notation. Okay. I want to put this on its own page. Maybe I'll put it here. Put her there. Okay. So the next example, the following relations are on the set 1, 3, 5. It's 3 itty bitties. Let R be the relation XRY if and only if Y is equal to X plus 2. And S is the relation XSY if and only if X is less than or equal to Y. In the end, we want to list all the elements in RS, all right? And then we're going to list all the elements in SR. I think it's going to be helpful if we list all the elements in R and then all the elements in S so that we can kind of see them. Yeah. And so here, let's start with, we've got the set 1, 3, 5. Let's start there. That's a weird curly bracket. Hey. Okay. And we have X, R, Y, if and only if Y is equal to X plus 2. So R then, let's do R in green, is going to be the set, and all I'm going to do is I'm going to work through each of the X's, right? But it also has to be a Y in here, right? And visually it's going to be the set A and the set B just have the same entries, 1, 3, 5, 1, 3, 5. And so if I take 1 plus 2, that makes 3. So that 1, 3 is in R. 3 plus 2 makes 5. And so 3, 5 is in R. I don't see any other options. 5 plus 2 is 7, and 7 isn't in the set. So I'm out. Huh? Okay. And I'll make this green as well. Now let's look at the relation S. XSY if and only if X is less than or equal to Y. So XSY if and only if X is less than or equal to Y. So S less than or equal to, and I shouldn't write it so sloppy. 1 is less than or equal to 1. 1 is less than or equal to 3. 1 is less than or equal to 5, right? So those are all entries in this relation. So let's jot those down first. 1, 1, 1, 3. I flip-flop. Sometimes I list all the equal ones to kind of get them out of the way. Doesn't matter. Order doesn't matter in a set, right? Okay. Now moving on to 3. 3 is less than or equal to 3, and 3 is less than or equal to 5. Oops. And 3 is less than or equal to 5. That's probably why I often list kind of the 1 goes to 1, 3 goes to 3, and 5 goes to 5 first, because otherwise I tend to forget them. And so finally, 5 is less than or equal to 5. So if we want to look at RS, right? I can start at 1 and get to 3, and then I need to look for first entries of 3, and I get 1, 3 or 1, 5, right, through 3. And then I could start at 3 and I can go to 5, and from 5 I can just go to 5. Right? So let's see here. Do you want to draw it, or should we list the entries? I guess I should have said first. We're going to do both. I know, but the way you said that, so. But we'll do both. So in RS, the composition RS, I have to start in R and I have to move to S, right? Then we're going to do SR, which of course I have to start in S and end up through R, right? List all the elements in RS. That's what we're doing. So I had 1, 3, and from 3 I can get to 3, 3. Or I can have 1, 3, and 3, 5. Or I can go from 3, 5 through 3, 5 to 5, 5. So RS is going to be the set of 1, 3, 1, 5, and 3, 5. What about B? SR. So now we're working the other way. Right, I can start at 1 and then I look for a gateway 1, which I have, so 1, 3, but that's it. And then let's see here. 1, 1 and 1, 3. One, 3, and from 3 I can go to 3, 5. From 1, 5, I'm stuck because I don't have a first entry 5. 3, 3, I can go from 3, 3 to 3, 5, so ending up at 3, 5. 3, 3, and 3, 5. From 3, 5, again, I'm stuck because I don't have a first entry 5 here, and same thing, 5, 5. I don't have a first entry 5, so I'm stuck. So SR is the set 1, 3, 1, 5, 1, 3, 1, 5, and 3, 5. Looks good. How about if we had to draw it? Right, we can visualize this thing. Let's use a different color. Make it nice and big here. 1, 3, 5. From R. 1, 3, 5 again. And then I can go through S into 1, 3, 5. What color did I use for R? We had, R just had 2 entries, 1, 3, and 3, 5. I'm gonna steal it from here so I don't have to scroll around so much. S took 1 to 1, 1 to 3, 1 to 5. Did them in a different order. 3 to 3, 3 to 5, and 5 to 5. You can go through and you can highlight the paths that work, right? 1 to 3 to 3, and 1 to 3 to 5, or 3 to 5 to 5. Same thing. Now, if you want to be kind of cheeky and you want to do SR, couldn't you just kind of put another block of 1, 3, 5 here and do your R, and then just pretend that you're starting here and see what it looks like? You can. So then 1, 3, 5, if you wanted to visualize it. 1 to 3 and 3 to 5. And then you would highlight the ones that work. You can get from 1 to 3. You can get from 1 to 3 to 5. And you can get from 3 to 3 to 5. It doesn't matter, as long as you're able to give me what the composition looks like, it's fine. So whichever way makes more sense to you, I'm happy with that. But I want to give you options. Options. Oops. Bonus. We're spending some normal time on it. Yeah.
Is RMS always going to have the same elements of it?
No, this is a simplified version where we just used, do you mean like here, what the same set that we're mapping from?
Like we ended up in with RS being 1, 3, 1, 5.
Oh, not necessarily. Yeah. 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 Good. No. The answer is no. This is a dove above. So a common way that we can kind of visualize relations is through what's called a digraph, or directed graph. Yeah, directed graph. We just call them digraphs, so that's what I had to think about. What does it stand for? And so if we have, a digraph, for example, if we have a set A, 0, 1, 2, 3, and this is some relation on A, okay, then what we can do is we can represent this relation as a graph. Okay? And so elements of A are called the vertices of the graph. And what we're going to do is we're going to represent the parts of A, or the elements of A, as nodes, right? And so kind of small circles or just dots or whatever you want. Then you're going to connect the vertex A, so a vertex or a node, to vertex B with an arrow, which is called an edge, if and only if A, R, B. So if A maps to B through R. Okay. And so what I want you to try to do is try just drawing a digraph for R. I will set you up in, I guess I'm gonna set you up for failure a little bit. No. Should I do the successful one, the nice looking one? I bet you wouldn't choose, whoops, especially there. You wouldn't choose to draw your vertices like this, right? But we need a vertex for each element of A, 0, 1, 2, 3. And so here I've placed them like this because it kind of makes the nicest look, or one of the nicest looking graphs. But I'll show you that you can draw them any way you want. So the rules are these. Now you connect these with a one-way arrow. If you can start from one and end up at the other. Okay. I guess I'll give you the 0, 0, 0, 0 is called a self loop. So it just loops around on itself and we do draw it. Hey, I thought I was gonna just let you guys do it. There. So that's a self loop. So we do show the self loop because the others don't have it. And usually it looks a little bit nicer than that. But give it a whirl for 1 minute. Uh, 0 goes to 0. We already tackled that one. 0 goes to 3. All right. One-way ticket. 1 goes to 2. Fair enough. 2 goes to 1. Now I'm going to draw both of those arrows, and I want you to as well. Usually we kind of draw them a little bit kind of curvy around each other, just to emphasize that they're kind of going different directions. There are simplified diagrams where if that's the case, if they're going both ways, then you only draw one. But for us, we're gonna kind of call it quits here pretty quick. So we're gonna draw both the arrows. Okay, so I've done 2, 1. How about 3 maps to 2? And 2 maps to 0. So the direction of the arrows matters, of course. And that's it. There's the digraph. Now, usually, like I said, I don't think it's intuitive to start with 0, 1, 2, 3 and draw them this way. So let's just have a look at what it would look like if we started with how, at least I intuitively would have put these 0, 1, 2, 3. Or is there any other way that you would have put them, just if you had to chance it? I just think I think it's just how I like to read left to right and then go down on the next line, 0, 1, 2, 3. Maybe if you're super into trig, you might have gone like 0, 1, 2, 3. No, I don't know. This to me, I think is my go-to. So let's draw it. It's still gonna work. 0 goes to 0, self loop. 0 goes to 3. 1 goes to 2. 2 goes to 1. 3 goes to 2. And 2 goes to 0. It's not that bad. Right? These show the same relation, right? And so the same relation is shown, just different digraphs. Usually what we end up doing is we draw kind of something like this, and then we take a step back and we try to figure out a way where we could maybe draw these without the overlap, right? Because this crossing over to 3 kind of makes a mess. And so one thing that I see here is, what if I just kind of swung the 3 over here? I could do that. And to kind of clean this up a little bit, right? You don't have to. It's just if it's hard to look at. So maybe I'll do this in, you could swing it over there and it would take those 2 lines with it. But it doesn't matter. Yeah. So sometimes if I'm nice, I'll tell you where to put the nodes, right? Or I'll have placed them for you. Okay. So 2 graphs of a relation can look very different, but as long as the connections are the same, it's describing the same relation. What if I give you a digraph and I want to know what information is it giving us? So a relation S on A is shown here. So I want to know about A, and I want to know about S. Luckily, you have it in front of you. Printed kind of small. But what are the elements in A? Well, they must be the nodes. 1, 2, 3. What's in the relation S? This is where you want to kind of be methodical again and kind of pick away at these arcs or edges one by one so you don't miss any. Maybe kind of check them off or something. And so I'm going to start just moving across, and then, or you can start at 1. You've got options. As long as you list all the coordinates, that's fine. Maybe that's what I'll do. I'll pick away at the 1 node. So 1 maps to 2 and 1 maps to 3. 1, 2, and 1, 3. So that means this one is done and this one's done. Oops, I'll just kind of.
Order matters.
Not in a set, no. Well, in the X, Y's it matters, but not between these coordinates. Or points, rather. Moving on to 2. 2 maps to 1 and 2 maps to 3. 2, 1, 2, 3. That one's done. This one's done. Finally, 3. 3 maps to 1 and 3 maps to 3. And that's all of them. And I'll erase these lines because it might not make sense later. So you should be able to move between from a digraph to information like this, right? The set A and the relation, or if I give you the set and the relation, you should be able to draw a digraph. Now, there are examples here. I'm gonna let you try them on your own because we've got some terminology mania here going on. So on the next page that we need to get through, or at least talk about, so you can try those examples. And I think they're just drawing digraphs. And again, there's lots of different ways that you can do it, but you can use those for practice. Okay. Here we have some definitions. A reflexive, hey, pointer. A reflexive relation, if A is a set and R is a relation on A, then R is reflexive if and only if A are A for all A in A. Haha. It's a cruel trick. What does that mean? If A is related to A, right, then that sounds like a self loop to me, right? In fact, it's a reflexive relation if all nodes have a self loop. And so that's what that really is saying. If all nodes have a self loop. Most relations are not reflexive, but some are. So you need to know what it is and how to determine it. Probably a matter of some memorization. Some of these are easier than others. For example, antisymmetric, I think is kind of telling in the name. Antisymmetric, if you have a set A and R is the relation on A, then R is antisymmetric if and only if whenever A is related to B and A is not B, then B is not going back to A. Okay, and so one-way tickets only is what that means, right? So if you have a link between A and B, then it's only antisymmetric if B doesn't go back to A. Okay. For any link A, R, B. This means we can only have a one-way arrow. If there is an arrow. Ugh. We can talk about ARB and BRA is only antisymmetric if A is equal to B, but let's just kind of skip that. You can read this and just kind of, I love it when they say stuff like, you're encouraged to convince yourself of this thing. That's kind of hard to wrap your head around. Don't worry about it. As long as you understand that it's a one-way ticket only, then that's what antisymmetric means. If there is a line, you can't have one going back. A transitive relation If R is transitive, if and only if whenever A are B and B are C, then you can get from A to C, right? It's kind of what we saw with those compositions, right? And so if you're able to go from A to B, and you're able to go from B to C, then in order to be transitive, then you must also be able to get directly from A to C. And that's where matrices are going to come into play. What? I know, right? Pretty cool. So, all right, because that's really hard to see. We go back to our example here, even one like this, I have a really hard time looking at this and saying, okay, I can go from 3 to 1 to 2, but I can't go from 3 to 2. I can go from 2 to 3, but in order for it to be transitive, I would need to add a link from 3 to 2. Okay. That for me is really difficult to be able to catch all of them, and so that's where matrices are really helpful, because then you know you've covered all of them. So what's a partial ordering? Partial ordering is a relation on a set that's reflexive, antisymmetric, and transitive. So it has to be this trifecta. Reflexive meaning all of them have self loops, antisymmetric meaning one-way trips only, and transitive means if you are able to go through a stop, you should be able to get there with a one-way or a direct flight as well, right? Kind of a stopover direct flight situation. Okay. So that's what a partial ordering means. How about a symmetric relation? R is symmetric if and only if whenever A are B, so if you can go from A to B, you must be able to also go from B to A. And this is where they kind of talk about, okay, anti-symmetric and symmetric, they're not opposite of each other, but for our purposes, they kind of are. So if it's symmetric, it's going to be symmetric. If you have a trip from A to B, then you must also include a trip from B to A. It's more fun to think of them as trips, I guess, instead of relations, but they could be trips. So here it would look something like this: A to A, A to B. Then if I have A to B, then I must have a B to A as well. An equivalence relation is if it's reflexive, so all the nodes have self loops, symmetric, and transitive. So just kind of slightly different from the partial ordering, which was reflexive, antisymmetric, and transitive. So if it's reflexive, antisymmetric, and transitive, then it's a partial ordering. If it's reflexive, symmetric, and transitive, then it's an equivalence relation. That's just kind of definitions that we need to practice and work on a little bit. And there's a whole page of practice that I'll leave for you. I'll post solutions. Okay. Here we have a relation on ABC. To really zoom in. Is it reflexive? No, right? I have a self loop on B, I have a self loop on C, right? But no self loop. No self loop on A, or I guess it's a lowercase a. It is not anti-symmetric because, well, I've got a one-way ticket from A to C, but I also can get from C to A, right? Let's see here. ARC and CRA. Right here, this is the problem for the anti-symmetry. It's not symmetric either. If it was symmetric, what would you need to make it symmetric? You would need to add a trip from B to A. We're not concerned about B to C because there is no line there, right? But for symmetry, if there is a line, there has to be a matching line. Okay. And so it's not symmetric because we're missing B to A, BRA here. It's not transitive. Here we're told that it's not transitive, but why? Can you see of a layover flight that doesn't have a direct flight? Yeah. So I can go from C to A to B, but that means that I should be able to go directly from C to B and bypass A, but I can't. CRA and ARB, but missing, I'll say missing CRB. Even if we didn't have a good handle on these definitions, we know that in order to be an equivalence relation, oh, I guess it's called S. Sorry, I missed that. I was using R. Hey, they never called it that, but so I'm just gonna change it here to R. That's convenient for me, right? They never defined it. Oh, right there. Well, I changed it to R. So I don't need to change it everywhere. Sorry, I missed that. What does it mean to be an equivalence relation? Right, it means it's reflexive, it's symmetric and transitive, but immediately we decided it's not reflexive, so it can't be an equivalence relation. But reflexive was also part of being a partial ordering, and so it's neither. Neither. And you can kind of talk your way through the definition there.
Also, I have to say ERC, not CRC on the transitive.
C gets to A and A gets to B, but I also need C to B.
Since ARB and BRC, then BRC of the. Or
Oh, yeah, but this is in general.
oh,
So if you're able to go from A to B and you're able to go from B to C, then you also must be able to go from A to C if it's going to be transitive.
and go all the way around as well.
Yeah, there's probably a few in here. I think the most obvious trip is from C to A to B. But then I would need to be able to go from C to B. Maybe there isn't another one. No other troublemakers that I see, but like I said, I have a really tough time seeing these transitive ones that are missing, so we'll rely on matrices. Okay, so this one, it just has a bunch of digraphs for you to practice, and I've got the solutions, so I'll post the solutions. How am I doing for time? Hey, perfect timing, okay. Because now we're gonna talk about, because those definitions, you just need to sit down and kind of work at them. And me reading the definitions to you is not super helpful, telling you what's what, but I'll post the solution so you can work through it. An adjacency matrix, finally some matrices again, right? If we have A with the set A through with m elements and B has n elements, then they have cardinality m and n, which we can form a matrix with. If R is the relation from A into B, then we can define a matrix, which we use capital R to denote a matrix, right, for the relation R. And we're going to jot down a 1 if A is related to B, right, and 0 otherwise. And so this is what's called an adjacency matrix, or the relation matrix of R, but I like to call it an adjacency matrix. Okay, now let's do an example where you're going to construct the adjacency matrix for the relation. Now, it's not obvious, but we're going from A into A. So if you're only given one set of elements, then you're going kind of from itself to itself. I'll get you set up here. I find that it's helpful to jot down the elements in the rows, but also in the columns, because then what you're going to do is, if there's a relation, you put down a 1, right? And you're always going from the rows to the columns. Okay? So here, this is row 2, column 2 gets a 1. So 2 goes to 2, 2 goes to 5, gets a 1. 5 goes to 6, and 6 goes to 6. Often I'll write down just the 1s and not worry about the 0s until the end, and then I fill in the 0s when I've written all those values down. So this is another way that we could visualize or summarize a relation. Okay. So if this is R, and what if I wanted to talk about R squared, which I could do? R squared is just a composition, so R is R squared. R is R squared. So we could sheet and copy because I can. R. And if I want to make the composition of RR, then we know how to do that, right? Oh, sorry. Two to two, I can get to 2. Oh, low battery. Oh no. Don't worry, guys. I'm prepared. It was only 10% anyways. I feel like I could get through it in 10%. If percentages were time, right? I feel like that should be a poem. If percentages were time. Well, they kind of are. There, that's the end of the poem. 2 goes to 2. And so 2, 2 is in my composition. From 2, I can get to 5. 2, 5 is already in the composition. From 2, 5, I can get to 2, 6. That's a new one. Right. Because I went from 2 to 5, then 5 to 6. So in the composition, I have 2, 6. Then I can go from 5, 6 to 6, 6. So 5, 6 is in my composition. And from 6, I can go to 6, I can go to 6, I can go to 6. So 6, 6 is also in my composition. But now I have this added value of 2, 6, which wasn't in my original relation. So I can rewrite my adjacency matrix with this 2, 6, right? Because this was 2, 5, 6, 2, 5, 6. And so this little guy is in there.
How do you justify those ones and zeros?
Do you mean like up here? By the definition. So if A is related to B, then you put a 1 in the adjacency matrix. Right? But you have to read it as the rows to the columns. Okay. And maybe I should clarify that here. Row, column. Okay. Back with matrices, feels good. We did not write R squared, just for notational purposes. R squared is R, the adjacency matrix, times R, the adjacency matrix. But we're going to use Boolean arithmetic, right, which does simplify things a lot, right? And so just for a little bit of review, we've seen it a couple of times before, right? But in Boolean arithmetic, we're stuck in a 0, 1 situation. And so 0 plus 0 is 0, 0 plus 1 is the same as 1 plus 0, which is still 1. 1 plus 1 is 1. So as long as you have a 1, you get to 1 essentially. And if it's all zeros, if you're multiplying by 0, you get 0, and 1 times 1 is 1. Okay, so composition is matrix multiplication. So if we have A1, A2, and A3, where R1 is a relation from A1 into A2, and R2 is a relation from A2 into A3, so we have that kind of same cascading relationship. If R1 and R2 are adjacency matrices, then the product R1, R2, using Boolean arithmetic is the adjacency matrix of the composition. So if you have the adjacency matrices, you can multiply them together to find the composition. So what does that look like? I'm just gonna copy both of these. This is R and this is S. So R times S is this thing. And Boolean arithmetic. Here we go. First row. Well, first of all, this is a 4 by 4 times a 4 by 4. I'm expecting a 4 by 4 matrix. Yeah. So I'll make room for a 4 by 4 matrix. That's helpful to know. And the first entry, first row, kind of overlaid with the first column and add them all up. Now what's really nice is the first column is all zeros, so it doesn't matter. I'm just going to overlay it with all zeros and I get a 0. So kind of way quicker math than what we had last week. For the next entry, I move over and I overlay this. 1 times 0 plus 1 times 0 plus 0 makes 0. Moving on. 0 times 1 is 0. 1 times 1 is 1. Cha-ching. Because how does Boolean arithmetic work? Well, as soon as I have a 1, 1 plus 0, it doesn't matter how many ones I have, I can stop. I have a 1, right? And so this combination here of 1 times 1 just gives me 1. So that means I can stop, right? And you can work it out, but eventually you'll kind of get lazy like me and say, oh, well, I'm able to see a matchup of 1 times 1, so I'm going to get a 1. Right? You can work through it properly, right? But the beauty of Boolean arithmetic is that it's so quick. As soon as you have a 1, then you have a 1. Move on. Okay, same thing. For the next row, we start over. All zeros again, no surprise. Now this 1 is overlaid with this 1, and so I'm going to get a 1. Score. Same thing. This 1 is overlaid with this 1, so I get a 1 again. And same thing with the next one. Right. So I get a 1 again. As long as you work methodically, it's not too bad. Well, the first one's boring because it's just 0. Second column, I've got a 1 followed by a bunch of zeros, and so the first term is 0 times 1, and so that was my only hope, right? And so I'm at 0. Now I see a 1 overlaid with a 1, so that's good news. I get a 1. And 1 overlaid with a 1 again gives me a 1 again.
That's only the goal. Orderly. You know, 1 at the very first row or first column.
Well, so what I'm doing in my mind is I'm taking this guy here and I'm overlaying it on top, right? And so then I see, okay, 1 times 0 is 0. 1 times 1 is 1. So that's what I'm latching on to. And then that makes the 1. because then 1 times 0 is 0 and 0 times 1 is 0.
Yep.
So it would be 0 plus 1 plus 0 plus 0. Makes 1.
0, 0, 1, 1.
You mean here?
Yeah.
That's just to get this number. So to get this number, you need to be in that row and that column. But you get pretty quick when it's Boolean. So for the last one, right, notice how I've stopped writing out or highlighting the columns, right? Just kind of work through the columns. And so timber on a bunch of zeros makes a 0. 1 in the first, right here, this is my only chance at getting a 1, but I have a 0 here, so that makes 0. Here, I have 2 chances and then another chance here, but there's no overlap. And so then it makes a 0. And finally, I see 1 overlap here and I get a 1. So then this is the composition of RS. Now I'm gonna just write out what SR is. I'll just give it to you so we can move on. 1, 1, 1, 1, but I do want you to practice it. 0, 1, 1, 1, 0, 0, 1, 0, 0, 0, 0, 0. Do you guys work with relational databases yet? Maybe not yet. I'm sure you will though. Here's how they work. Maybe not how they work. One aspect of relational databases. And so a relational database program has just information stored in matrices, right? And so here we have some matrix R and some matrix S on the right. It's kind of crossing over. Oh, and I drew in your notes computer C because it got loaded over here. Computer C. But then I went really old school and I wrote it in your notes and then photocopied it. I know, still works. Okay. And so here we've got program 1, 2, 3, 4. It runs or doesn't run, depending on the zeros and ones, on operating system 1, 2, 3, 4. Then I have another database where I know the operating system that runs on each computer, computer 1, 2, 3. Okay. And so here, of course, you could kind of individually look at, okay, does computer 3 run program 4, for example, right? You could kind of get there. Okay. But in order to answer kind of more complicated questions, you would need to do some matrix multiplication, right? Because this is just a composition, right? Has to be R, then S, right? And those both have to be satisfied. Okay, so what can we do? What can we do? I can first check to make sure that the dimensions work, right? Here I have a 4 by 4 matrix. This is a 4 by 4 matrix, and I'm multiplying it by a 4 by 3 matrix, which will give me what? It's going to give me a 4 by 3 matrix. Oops. And I'm just gonna copy these because I don't want to write them all out again. Copy. So this is R and this is S. Something like that. And we want to multiply the two. Can do the same thing again, right, that we were doing. And just remember that we're gonna get a 4x3 matrix. I want you to try it. I'll give you the answer so we can talk about it, but I do want you to try it for practice because it's going to be really useful. The result is going to have program 1, program 2, program 3, and program 4 in the rows, and computer 1, computer 2, and computer 3 in the columns. So now all of a sudden you have that kind of gateway from the program to the computer through the operating system. So the answer is this: 1 1 1 1 1 0 0 1 1 0 1 1. That tells me that all the programs will run on all the computers except, therefore, all programs run on all computers except P2 on C3 and P3 and P4 on C1. They should just ditch computer 1 then. Can't run anything. So here, right, I want you to try that, but me doing matrix multiplication is pretty boring watching me do it. So you can try it. We can have a relation just like we did, and we can find the adjacency matrices, and we can do what we did before with the composition, where we said, okay, I have to start here and end up here to find the composition. But I also want you to try it with the matrix multiplication. How about the transitive closure? So if we have R as a relation on A, then the transitive closure R is denoted by R plus. Well, that's the transitive closure of R. And it's the smallest transitive relation that contains R as a subset. So a transitivity, remember, is if you can get there through layovers, you have to be able to get there with a one-way direct flight as well, right? And so how can we figure out all the missing flights, if you will, that we would need to add, right, to get the smallest transitive relation possible? So if we have, oh yeah, first an example. If A is 1, 2, 3, 4, and S is this relation 1, 2, 2, 3, 3, 4, this relation is called a successor relation. That's not important because each element is related to its successor. And so how are we going to compute the transitive closure on this thing? So you could work through and you could say, okay, well, I see that I can go from 1 to 2 to 2 to 3, so, but I'm missing 1, 3, so I would need to add that in, right? Or I could go from 1 to 2 to 3 to 4, so I would need to add 1, 4, right? It doesn't just have to be 2 flights, it can be 3 or 4 flights. Okay. I can go from 2 to 3 to 3 to 4. We see that there are a lot of kind of missing coordinates. We notice many missing coordinates for transitivity. It can be done, but it's easier with matrices. And so what we're going to find in the home stretch of today, I know, if we have a relation on the set A and A has cardinality n, right? And so in this case, A has cardinality 4. Then the transitive closure of R is the union of the first n powers of R. So you would need to, right, because we're allowing multi-stop trips, but they have to be linked with a direct flight, essentially. And so that's why you have to allow for n times, right, n flights. And so what the transitive closure is going to look like is you take your first relation and then you go through R again, R squared, then you go through R again, R cubed, all the way up to Rn. The union just means that you're going to put them all into one set, right? Or this, or this, or this. Easier with matrices though. The matrix of a transitive closure says that, okay, the matrix that you're going to find, R plus, is going to have the initial R, the adjacency matrix. You're going to find R squared, right? R times R. Then R to the 3, R to the 4, all the way up to R to the n, and then add those all up using Boolean arithmetic. So it's going to be the sum of all those powers. I will get you to do that, but I'll make sure it's a tiny set A, right? For example, I think 4 is maybe even too much, right? Maybe it's just right. You can do 4 multiplications and then add those all up, right? Adding matrices is easy, especially with Boolean arithmetic. If there's a 1, you have a 1, you have a 1, you have a 1. Okay. So you're going to find each of those matrices, right, up to the power of however many elements you have in the set A. And then you add those all up, and the result is the transitive closure of R. I'll leave these last 2 examples for you to try. And with that, I release you. If you have any questions, let me know. Otherwise, see you on Friday. We'll do test review on Friday.